Vacuum interrupters are widely used in medium voltage circuit breaker.
But how does it work?
Let's spend few minutes to boost your knowledge about them.
And first, let's have a look inside.
A vacuum interrupter is composed of two contacts to make and break the current through contact tips made of a special composite material. They are made of a sintered mix of chromium and copper powders.
There is a fixed contact and a moving contact.
The two contacts are separated by an insulating body, which could be made of one or two ceramics.
The fixed contact is linked to the ceramic through the fixed and side cover.
And the moving contact is linked to the ceramic through the metallic bellow and the moving end side cover.
There is a shield around the contact, which will collect the metallic vapor released during a breaking operation to avoid the contamination of ceramic.
This shield could be polarized, means is linked and at the same potential to the fixed contact,
or at floating potential, and fixed between the two ceramic bodies.
To operate a vacuum interrupter, we just have to pull on the moving contact, usually around 10 mm for application up to 24 kV.
If we release the moving contact, it closes thanks to the atmospheric pressure applied to the bellow's base surface.
So, is it filled with a vacuum?
In fact, vacuum is space devoid of matter.
So, we need to extract matter, and it will be filled with nothing.
Well, almost nothing, as real vacuum doesn't exist in our world.
The quality of vacuum can be specified in several manner.
We can define it as the average number of particles in a cubic centimeter,
or give a value of remaining pressure, usually in millibar, but Pascal and torr are also used.
We can also define the mean free path, which is the statistical path's length a particle can travel before colliding in another one.
Indeed, higher is the pressure, more their particles, and shorter is the mean free path.
What vacuum for a vacuum interrupter?
At the Earth's surface, we have a pressure of 1 bar, which is equivalent of 10 power 19 particles per cubic centimeter.
In Moon's atmosphere, we have only 100,000 particles per cubic centimeter.
A new vacuum interrupter has a pressure of 10 power minus 6 millibar, which is equivalent of 10 power 10 particles per cubic centimeter. We found this gas density around 300 kilometers away from the Earth.
A bad vacuum interrupter has a pressure of 0.1 millibars, or 10 power 15 particles per cubic centimeter, which is equivalent to an altitude around 50 kilometers. So, why a vacuum interrupter needs to be at a maximum pressure of 0.01 millibar? Because above this pressure, we have enough gas to experiment a phenomenon, which is called gas breakdown.
We are going to explain it now.
Let's see what happens between contacts of vacuum interrupter.
In this example, we sketch a vacuum interrupter with a 10 mm gap, a pressure of 1 millibar, and a voltage between electrodes of 28,000 volts.
A particle is excited and liberates an electron.
This electron accelerates toward the anode, and collides in a particle with enough energy to extract another electron from it. These two electrons collide into other particles, and so.
We have an electron avalanche or a Townsend discharge, which cause a gas breakdown.
Now, let's raise the pressure to 1 bar. We reduce the mean free path so much that a free electron cannot accelerate enough before it collides with a particle. As it does not have sufficient kinetic energy to release another electron, the free electron bounces from particle to particle on his way toward the anode, without ionizing particles.
There is no gas breakdown.
Last, let's reduce the gas pressure under 0.01 millibar. The mean free path is greater than the distance to the anode,
and any free electron reaches the anode without any chance of collision with a particle.
There is no gas breakdown.
These different phenomena could be observed on the Paschen curve.
This one is drawn for a gap of 10 mm in the air.
We can observe that the dielectric withstands at atmospheric pressure is around 30,000 volts for a 10 mm gap.
The worst dielectric withstand is around 1 millibar, only 300 volts for a 10 mm gap.
Under 10 power minus 2 millibars, the dielectric withstand is around 200,000 volts for a 10 mm gap and become independent from the pressure. If there is no Townsend breakdown under 10 power minus 2 millibars, what limits the dielectric performance to 200,000 volts for 10 mm gap?
Other phenomena limit the dielectric withstand. The two most important are the field emission and the detachable particles.
Field emission describes the phenomena of electron emission from the contact material in presence of a very high dielectric field.
Indeed, the vacuum interrupter is designed to avoid the high dielectric field.
Nevertheless, on a microscopic view, there is a lot of spot on the surface contact. Around these spots, the dielectric field could be 100 times higher, which trigger electron emission.
Local high electronic current flow heats the spot.
It be vaporized in metallic ions and triggers breakdown.
It is interesting to notice that this process will remove the spot and restore dielectric withstand.
Detachable particles are particles present on the contact or shield surface are set free after mechanical vibration or electrostatic forces.
They accelerate in the intercontact gap and collide with an electrode with enough kinetic energy to emit ion by local vaporization of the contact and the particle itself. This local ionization can trigger a breakdown.
In addition to this phenomenon, the particle can also start the field emission process.
A vacuum interrupter interrupts current when it crosses zero.
After contact separation, small arcs are created between contacts to let the current flow.
Above around 8,000 volts arcs constrict in one, which needs to be controlled in a way we will see later.
Under 8,000 volts arc separates itself into small arcs.
And close to zero it will stop and interrupt current.
A vacuum interrupter can interrupt current independently of motion. It needs just enough gap to withstand the transient recovery voltage. For 12 kV only 3 mm.
To avoid a constrict arc to erode too quickly the contact tips, there are two possibilities.
Radial magnetic field is the first one.
Take the example of these spiral contacts.
When the arc is initiated, the current flow creates a loop which generated a magnetic field B.
Using the rule of the three fingers we can define the direction of the force applied to the arc itself.
This force makes the arc turning around the contact and avoid localized erosion. Only the contact trims will be used.
Obviously, when the current change direction, the magnetic field change as well, and the force stay in the same direction.
Another type of radial magnetic field could be made by using grooves on butt contact. Slots should be in the opposite direction to get the same effect as the spiral contact.
The second type of arc control using similar contact to previous one but with the slot in the same direction.
This creates a current loop around the axis of the interrupter, which lead to an axial magnetic field.
Under this magnetic field, the arc diffuses across all contact surface.
Erosion is spray across the whole contact area, which is more efficient than the radial magnetic field.
Of course, there is a lot more to know about vacuum interrupter and other topics on medium voltage, but it is just an example of what we can do.
So, contact us.